All right, welcome to the Explainer. Today, we're diving into the science behind one of the most powerful and surprisingly simple separation techniques ever invented, chromatography. So let me ask you something. Think about a single drop of black ink. To our eyes, it looks like just one solid color, right? But what if I told you it's actually a whole cocktail of different dyes, all hiding in plain sight? How on earth would you even begin to prove that? Well, the answer is a brilliant process called chromatography, and the name itself is a fantastic clue. It actually comes from two Greek words, chroma, which means color, and graphene, which means to write. So if you put them together, you literally get color writing. And that name makes perfect sense, because its very first use was for separating the vibrant colors from plant leaves. And get this idea isn't new. It's been getting refined and perfected for over a century. It all kicked off back in 1906 with Mikhail Zvet and his work on plants. Then, fast forward to the 40s and 50s, and we see these huge leaps, like partition and gas chromatography. In fact, gas chromatography was so revolutionary it even nabbed a Nobel Prize. By 1958, thin layer chromatography came along and made the whole technique way more accessible. It's just this amazing story of constant innovation. Okay, so how does this color writing thing actually work? What's the secret sauce? Honestly, the simplest way to wrap your head around it is to think of it as a race for molecules. In any race, you've got two key players. First, you have the racetrack. In science speak, we call this the stationary phase. This is the surface that stays put, the thing that doesn't move. A great example is a thin layer of silica on a glass plate. Then you have the current. We call this the mobile phase. This is the part that moves. It's a liquid or a gas that flows over the track and carries the mixture with it, kind of like a river. So here's the magic. This is what it all boils down to. Not all the molecules run the race at the same speed, and it's all because of something called affinity, which is just a fancy way of saying how much a molecule likes or sticks to the racetrack. See, components with high affinity really cling to that stationary phase, so they travel slowly. But the ones with low affinity, they barely stick at all and get swept along by the mobile phase, moving much, much faster. That difference in speed is what separates the whole mixture. Let's make this real with that ink example using thin layer chromatography. First, you put a tiny spot of the ink on the plate. That's step one. Next, you dip the edge of that plate into a solvent. That's our mobile phase, our current. And then the race begins. As that solvent starts to creep up the plate, it carries the ink along with it. But because the different colored dyes have different affinities, they separate out, fanning into these distinct bands. And just like that, the single black spot reveals its true colors. Okay, separating ink is a pretty cool trick, for sure. But why is this one of the most important techniques in all of modern science? Let's zoom out from the lab bench and connect this to our actual, everyday lives. The reason chromatography is pretty much everywhere is simple. It's just so incredibly efficient. It's often one of the simplest, fastest, and most cost-effective ways for scientists to pull things apart and figure out what's inside. Its real power is in just how accessible it is. And this tool is absolutely vital to modern life. I mean, we're talking about ensuring the purity of the medicines we all rely on. In forensics, it's used to detect drugs or toxins in a patient's blood. It's essential for the quality control of everything from the food we eat to the fuel in our cars. It's kind of like a silent hero, working behind the scenes to keep us safe. And this chart really just drives that point home. Whether you're talking about the high stakes of making sure medicines are pure, the critical answers needed in a forensic investigation, or the massive scale of industrial quality control, in every single one of these fields, chromatography is an absolute non-negotiable cornerstone. So if you take one thing away today, let it be this. Chromatography is like a scientific superpower. It's a method for making the invisible visible. It gives us this incredible way to deconstruct the world around us and understand what it's truly made of. Which leaves us with a pretty cool final thought to ponder. The air we breathe, the food we eat, the water we drink. What else in our world is a complex mixture just waiting to be separated and finally understood?